Passage containing question number 7 and 8. So this is question stem, and we need to answer question number 7 and question number 8, which are asking basically Q1 and Q2 values. Let's read. It says in the circuit shown below, so there is a circuit, we can see the switch as is connected to position P. So this was connected to position P for a long time, so that charge on the capacitor becomes Q1 microcoulomb in totality. Then the switch as is shifted to the position Q. So this is shifted to position Q. After again long time, the charge on the capacitor is found to be Q2 microcoulomb. So we need to find Q1 and Q2. So it's again basic question related to this capacitor and resistance circuits. So first it is connected, switch is connected to P for a long time. We know in long time capacitor is fully charged, so it does not allow any current to pass through. Circuit will become so this simplified because this S is connected to P, so there's nothing to do with this branch. So we can say this is the simplified graph. And the current will be moving in this outer loop only. This branch will not have any current through this. We can consider the current to be I, and we can go for the Kirchhoff's voltage law for that loop, and you'll find it's going to be like twice I, then 1I plus 1 minus 2 must be equal to 0 as per the Kirchhoff's voltage law. And then this will give us the value of the current, which is 1 by 3 ampere. So current running on this is going to be 1 by 3 ampere. We need to find the charge on the capacitor, so we need to know how much the potential difference across this capacitor is. Now potential difference across this capacitor can be calculated by using the loop equation or Kirchhoff's voltage either for the left or right loops, or maybe anyhow we can find it out this. So potential difference across this, we can use this loop. So we can say capacitor will have a potential difference corresponding to these two together. So potential difference across capacitor, let's say V is going to be like 1 into I plus 1. So that's how I write it, because this is plus minus, this is plus minus, so they are getting added up, right? And that addition is this. Now I can be substituted as 1 by 3, so that becomes 4 by 3. Now we know this potential difference across capacitor is going to be written as charge on the capacitor, which is Q1 divided by capacitance. From here Q1 is going to be equal to 4 by 3 microcoulomb, because capacitance is 1 microfarad. So that micro will be there, and farad into volt together make it coulombs. So answer comes out to be 1.33 microcoulomb. So that's Q1. That means that's answer of the question number 7. Now when this switch is shifted to this Q and time is allowed for a long time, so the circuit will become this much. That means 1 volt battery will not be in the circuit now. Again, we can think of after a long time this capacitor got charged whatever it is supposed to, and it's completely charged and no current is being shared or passing through this. So let's say I current, this is a different I for this particular case, and it is running in this outer loop. Go for the KVL, and the KVL will say 2I plus 1I is equal to 2. That is basically 3I is equal to 2. That is basically I is equal to 2 by 3 ampere. So this time current is going to be more as compared to the previous time, and it's going to be double basically. Now again we need to find the potential difference across capacitor. We can use this left loop, and we can say potential difference is going to be 1 into I, that's all. So I is this, so it's turned out to be 2 by 3 volt. We know potential difference across capacitor is equal to the charge on the capacitor, which is now Q2 divided by capacitance, which is the original one, right? So Q2 is 2 by 3 microcoulomb. So we got to answer that Q2 is going to be 2 by 3, which can be written as 0.6666, and we can round off as 0.67 microcoulomb. Hence we got Q2 as 0.67, Q1 as 1.33, and their units have been already mentioned, so we need not to worry, and we are writing in those units itself. Okay, thank you.